Preparing for a design engineering at LTTS interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. Walk me through your design engineering process from customer requirements to production. I begin by converting customer needs into measurable engineering requirements, including performance, cost, safety, and applicable standards. Next, I generate concepts, perform feasibility calculations, select materials, and create parametric CAD models. Design reviews help identify risks before prototyping. I then coordinate prototype fabrication, testing, corrective actions, and release documentation. Finally, I verify manufacturability, serviceability, and change control requirements. This structured process prevents late failures while keeping the design aligned with customer expectations. While answering, focus on requirement interpretation, concept generation, feasibility, calculations, CAD modeling, material selection, reviews, prototyping, validation, documentation, and design for manufacturing principles. Question 2. How do you select a material for a mechanical component? I select materials by first defining the component's loads, environment, temperature, life, and manufacturing process. For example, I compare yield strength, fatigue behavior, stiffness, density, corrosion resistance, and cost rather than choosing only the strongest material. I also check availability, heat treatment, surface finishing, and galvanic compatibility. A lightweight aluminum alloy may suit a bracket, while steel could be better for fatigue-critical joints. The final choice balances performance, reliability, manufacturability, and total cost. Make sure to cover mechanical properties, operating temperature, corrosion, fatigue, weight, manufacturability, availability, cost, surface treatment, regulatory requirements, and compatibility with adjacent materials. Question 3. What is GD&T, and how have you applied it in a drawing? GD&T communicates functional geometric requirements more clearly than coordinate dimensions alone. I establish datums based on how the part is located and assembled, then apply position, flatness, perpendicularity, or profile controls where they protect function. For a bolt pattern, position tolerance with a suitable datum scheme controls assembly accurately. I use MMC when bonus tolerance benefits manufacturing and inspection. Good GD&T reflects the functional stack-up and avoids expensive tolerances that do not improve performance. In your answer, discuss datum structure, feature control frames, form, orientation, location, runout, maximum material condition, functional intent, inspection methods, and avoiding unnecessarily tight tolerances. Question 4. How would you perform a tolerance stack-up analysis? I first define the functional requirement, such as clearance, alignment, or preload, and map every contributing dimension in the assembly chain. For a conservative design, I use worst-case addition of maximum variations. When variations are independent and statistically controlled, root-sum square analysis can provide a realistic estimate. I identify the most sensitive contributors and adjust dimensions, datums, or process capability. The result must satisfy assembly performance without forcing unnecessarily tight, costly tolerances. Be sure to mention worst-case and statistical methods, dimensional chains, contributors, datum references, assembly requirements, sensitivity, root-sum square calculations, and balancing performance against manufacturing cost. Question 5. What design for manufacturing principles do you follow? Design for manufacturing means making the product easy to produce consistently, not merely possible to manufacture. I choose the process early, use standard sizes and tools, reduce part count, provide adequate radii, and maintain suitable wall thicknesses. I also consider tool access, fixturing, inspection, material availability, and assembly sequence. For molded parts, I include draft and avoid sink-prone geometry. Early supplier feedback often eliminates expensive redesigns and improves quality simultaneously. Focus on process selection, minimizing part count, standard features, accessible tooling, consistent wall thickness, draft angles, bend radii, machining access, inspection, assembly sequence, and supplier capability. Question 6. How do you design a component for fatigue life? For fatigue design, I identify the actual load spectrum, cycle count, temperature, environment, and failure consequence. I reduce stress concentrations through smooth transitions, generous fillets, and appropriate surface finish. Using material SN data, I evaluate alternating and mean stresses, apply a suitable correction model, and select a safety factor. FMEA helps locate hot spots, but I validate assumptions with testing when risk is significant. I always consider manufacturing defects and corrosion because they strongly reduce fatigue life. Discuss load cycles, stress concentrations, surface finish, mean stress, material SN data, notch sensitivity, corrosion, safety factor, finite element analysis, testing, and identifying realistic service conditions. Question 7. How do you use FMEA during the design process? I use FMEA to answer a specific design question, such as stress margin, deformation, thermal behavior, or natural frequency. I define realistic loads and constraints, assign validated material properties, and create an appropriate mesh. After checking convergence and reaction forces, I compare results with hand calculations and examine whether stress concentrations are physical or numerical. I run critical load cases and sensitivity studies, then confirm important predictions through testing. FMEA supports engineering judgment, it does not replace it. Mention defining objectives, material properties, boundary conditions, mesh quality, convergence, load cases, contacts, result interpretation, hand calculations, sensitivity studies, and physical validation. Question 8. How would you investigate a component failure during testing? I would first contain the issue and preserve failed parts, test data, photographs, and assembly records. Then I would characterize the failure mode, such as overload, fatigue, wear, buckling, or manufacturing defect. I would reconstruct actual loads and environmental conditions, inspect dimensions and materials, and compare results with calculations or FMEA. Using methods such as 5 whys or a fault tree, I would identify root causes, implement corrective actions, and repeat validation before releasing the design. In your answer, cover containment, evidence preservation, failure mode identification, load and environment reconstruction, fractography, design and process review, root cause analysis, corrective action, and verification testing. Question 9. Explain the difference between a design change and an engineering change order. A design change is the technical modification itself, such as changing a material, dimension, or feature. An engineering change order is the controlled process that evaluates, approves, documents, and implements that modification. I assess impacts on fit, function, safety, cost, tooling, inventory, testing, and customer commitments. The approved change receives a revision, updated drawings and bills of materials, effective dates, and traceability. Strong configuration control prevents mixed versions from reaching production or service. Be sure to distinguish engineering intent from controlled release, and discuss revision levels, impact analysis, approvals, affected documents, configuration management, traceability, and communication to manufacturing. Question 10. How do you ensure proper fit and function in an assembly? I start by defining every critical interface, including location, alignment, clearance, load transfer, and required motion. I establish common datums, perform tolerance stack-ups, and select clearance, transition, or interference fits based on function. In CAD, I check interference, motion, access, and assembly sequence. Physical prototypes reveal issues such as tool access or distortion. I then define inspection points and assembly controls so the intended fit remains repeatable throughout production and maintenance. Discuss interface definition, datum schemes, tolerance analysis, clearance and interference fits, assembly sequence, fasteners, alignment, motion checks, prototype trials, inspection plans, and serviceability. Question 11. What factors do you consider when designing a sheet metal component? For sheet metal, I consider thickness, material, bend radius, grain direction, bend allowance, K-factor, springback, and available press brake tooling. I maintain practical hole-to-edge distances, add bend reliefs, and avoid features that distort during forming. I verify the flat pattern and ensure the bend sequence is physically achievable. Weld locations, access, surface finish, and inspection also matter. Designing around the supplier's actual tooling improves repeatability and prevents costly trial and error. Cover material thickness, bend radius, bend allowance, K-factor, grain direction, reliefs, hole-to-edge distance, springback, tooling limits, flat patterns, welds, and minimum feature spacing. Question 12. How would you design a bolted joint for reliability? I design a bolted joint by defining external loads, joint stiffness, required preload, and allowable separation or slip. I select bolt grade, diameter, engagement, grip length, and clamped materials, then check tensile, shear, bearing, thread stripping, and fatigue risks. Torque alone can vary because of friction, so critical joints may need angle control or direct tension verification. I also address locking, corrosion, access, and assembly repeatability. The joint must remain secure throughout its service life. Mention preload, joint separation, bolt strength, clamped member stiffness, torque control, friction, fatigue, thread engagement, washers, locking methods, corrosion, and applicable standards. Question 13. How do you choose between casting, forging, machining, fabrication, and additive manufacturing? I compare processes against volume, geometry, strength, accuracy, surface finish, lead time, and total cost. Machining suits low volumes and tight features but can waste material. Casting supports complex shapes economically at scale, while forging improves strength through grain flow. Fabrication works well for larger welded structures, and additive manufacturing is valuable for complex prototypes or low-volume parts. I also consider tooling investment, post-processing, inspection, and whether the chosen process can scale reliably. Focus on production volume, geometry, strength, dimensional accuracy, tooling investment, lead time, material behavior, surface finish, tolerances, lifecycle cost, and prototype to production strategy. Question 14. How do you manage conflicting requirements such as weight, strength, cost, and manufacturability? I convert each requirement into a measurable target and identify non-negotiable constraints, especially safety, regulatory compliance, and customer performance. Then I compare concepts using weighted criteria such as mass, strength margin, cost, lead time, and manufacturing risk. I use calculations and prototypes to reduce uncertainty rather than relying on opinions. When trade-offs remain, I present alternatives with quantified consequences and document the decision. A good design optimizes the whole product, not one isolated metric. In your answer, explain requirement prioritization, measurable constraints, trade-off studies, Pareto thinking, safety margins, cross-functional reviews, prototypes, and documenting the final engineering rationale. Question 15. Describe a time you resolved a disagreement with manufacturing or a supplier. In one project, a supplier reported that a tight profile tolerance was difficult to inspect consistently. I reviewed the functional requirement with them, examined process capability data, and separated critical surfaces from non-critical ones. We revised the datum scheme and tolerance specification without reducing assembly performance, then agreed on an inspection method and trial lot. The change lowered rejection rates and shortened lead time. I learned that collaborative, data-based discussions resolve conflicts better than defending the original drawing. Make sure to cover listening to the concern, verifying facts, reviewing drawings and process capability, using data, protecting functional requirements, agreeing on actions, and measuring the result professionally. Question 16. What is Design FMEA, and how do you use it? Design FMEA is a structured method for identifying how a design could fail before production or field use. I list functions, failure modes, effects, causes, and existing controls, then evaluate severity, occurrence, and detection or the organization's current risk method. High-risk items receive prevention or detection actions, such as stronger geometry, better sealing, or a validation test. I assign owners and update the FMEA as knowledge changes. It is most effective when linked directly to drawings and tests. Discuss failure modes, effects, causes, current controls, severity, occurrence, detection, risk prioritization, prevention actions, ownership, review timing, and connecting FMEA outcomes to design changes. Question 17. How do you verify and validate a new mechanical design? Verification asks whether the design meets documented specifications. Validation asks whether it solves the customer's real need in its intended environment. I create a requirements matrix linking each requirement to analysis, inspection, or testing. Before testing, I define acceptance criteria, instrumentation, fixtures, load cases, and environmental conditions. I use representative prototypes and record deviations, failures, and corrective actions. Final approval requires objective evidence, traceability, and confirmation that all high-risk requirements are satisfied. Be sure to distinguish verification from validation, and include requirements traceability, analysis, inspection, testing, representative conditions, acceptance criteria, instrumentation, failure documentation, and final sign-off. Question 18. Which CAD practices help you create robust, reusable models? I build CAD models around design intent rather than simply reproducing current dimensions. I use stable datums, fully constrained sketches, meaningful feature order, and parameters that reflect likely changes. I avoid fragile references, unnecessary external links, and excessive detail in large assemblies. Standardized naming, configurations, reusable templates, and associative drawings improve team productivity. Before release, I check mass properties, interference, manufacturability, and model health. Good CAD should make future revisions safer and faster. Discuss design intent, parametric features, meaningful constraints, master geometry, reference management, naming, configurations, assembly structure, lightweight models, drawing associativity, and revision discipline. Question 19. How do you prioritize work when supporting multiple LTTS customer projects? I prioritize work using safety, customer impact, contractual milestones, technical dependencies, and risk rather than simply responding to the loudest request. I break tasks into estimates, identify blockers, and maintain a visible plan with owners and due dates. For competing priorities, I communicate trade-offs early and confirm revised expectations with project leads. I protect configuration control and review quality even under pressure. Clear status updates and timely escalation help me support multiple customers without creating hidden delivery risks. Focus on safety and customer impact, milestones, dependencies, effort estimates, risk visibility, stakeholder communication, configuration control, escalation, and balancing urgent requests with planned engineering work. Question 20. Why do you want to join LTTS as a design engineer? I want to join LTTS because its engineering services environment offers exposure to real products, global customers, and varied domains such as automotive, industrial, and medical technology. That setting matches my interest in converting requirements into manufacturable, validated designs. I bring strength in CAD, engineering fundamentals, drawings, and structured problem solving, while remaining eager to learn customer tools and processes. I would contribute through reliable execution, clear communication, and designs that improve quality, cost, and time to market. Mention LTTS's engineering services model, exposure to global customers, multidisciplinary product development, quality focus, continuous learning, ownership, communication, and how your design skills can create measurable client value. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.